welcome back to another one of my applications of differentiation videos. This will be focusing on optimization and the first video. So let's begin with an example. Example 1. So we're going to start off with something basic for the first video, just a square or a rectangle, and we're going to have one side is going to be x and the other side is going to be a y. And say we're optimizing a paddock for a farmer who's in the middle of somewhere, and he wants the biggest paddock, so it's got to have the maximum area, but the constraint is that he only has 100 meters of fencing. Okay, so we have to use this 100 meters of fence to give him the biggest paddock that he can get. So this is where we optimize. So what we're going to do is first write the area, write the formula for the area, which is length times width, xy, because this is what we want to optimize. But we don't know x, nor do we know y. Now, the perimeter is equal to 2x plus 2y, because we have 2 y's and 2 x's. And because 100 meters of fencing is our constraint, 100 meters of fencing is the border, the perimeter is the border, therefore perimeter equals 100, because we've got 100 meters of fencing and the perimeter is going to be equal to the fencing, the amount of fencing. So now that means we have 100 2x plus 2y. So we can use this equation and rearrange it to find one of these values using the other value and put it into the area and solve. So let's get started. So I'm going to subtract 2x from both sides, which will leave me with 100 minus 2x equals, these will cancel out, 2y. Okay, and then what we're going to do is divide both sides by 2. That means this will cancel out. So we'll have on this side y, and this side 100 divided by 2 is 50, minus 2 divided by 2, that's 1, so it'll just be x. And now we have a function of y that has, we have a formula of y that uses x. Okay, so if we have a look up here, y is on its own, and here y is on its own. Well, not necessarily on its own, but you get the idea. So we have our area equals x, and because y equals 50 minus x, and we have a y here, we can sub this in, because y and 50 minus x are the same thing, hence the equal sign. So we can sub either the 50 minus x or the y in this spot here. So I'm going to sub the 50 minus x there, and then I'm going to expand it and get x, 50x minus x squared, and that will equal the area. Now, just to clarify what we're actually trying to do, so we have a box, and let's say it's based on x, which is this one, I think it was. Yep. So the graph, let me get my words. The graph will be x and the area. Okay, because the function is area and the variable is x. And it will look something like this. And that basically means when you have a small x value, the area is small. As you increase the x value, the area gets bigger and bigger, and then it starts going down again and becoming small. Now, that's basically saying, this is our x value here. If we were to increase this x value, that'd probably be somewhere about here or so, but the area would be very small. if we that'd be increasing the x value. That'd be over here. Sorry, this would be more like, that'd be that. That there would be more like this, which means the x value is very small and the area would be very small. What we want to do is go somewhere in the middle, which is about here, which should be something like this. That's in between this and this. We want the maximum area. We want the maximum area. I can't do a square in my hands. We want the maximum area from that square, because this is small because it's over here, and this is small, it's over here. This will sit somewhere around here. So we want somewhere, basically we're going to be finding a cube, but that's what we want to look for, something like that. A square. We're going to be looking for a square. So what we do to find the maximum point is we find that the derivative, because what we're looking for is this point up here. And if you found the derivative, the slope there would be 0. If you watch my video on critical numbers, the slope at the maximum or minimum point is 0. Okay? So, we find the derivative, that'll be 50 minus 2x. And then we let it equal to 0. We let the derivative equal to 0. Because that means we're letting the slope equal to 0. And which will be, at this point, the tangent line. So it's only going to pass through one point and the slope is going to be 0. Therefore, it's going to be at the maximum in this case. So we let it equal to 0. We get 0 equals 50 minus 2x. Get rid of that. Add 2x to both sides. 2x equals 50. Divide by 2. We get x equals 25. And write meters. Okay? Which makes sense. Followed by the next bit. Now we have an equation here. It's at the top. we have y, but we need x to solve. Lucky we found sorry. Lucky we found x. So y equals 50 minus x. Let's put that in. Grab another piece of paper. Y equals 50 minus x. X equals 25, so that's 50 minus 25 is y. Therefore, y is equal to 25 meters. Which is great. 25. That means that it's going to be a square. Which makes sense, because if x gets bigger and y gets smaller, then the area is going to be smaller than if it was a square, because a square is optimized. It's I won't gibber on too much. I don't want to confuse you. But so now the area equals x and y. We've established that x is 25 and y is 25. Therefore, the area equals 625 meters squared. And if you were to change the values and do this in your own time, you would find that if you increase the y value and decrease the x value, the area wouldn't be as great. And if you increase the x value and decrease the y value, the area would still be smaller. This is the biggest area. This is the most area. I don't know if I'm saying that correctly, but this is the most area you're going to get out of using 100 meters of fencing, basically. Anyway, I hope that helped you in some way. Thanks for watching and have a good day.